At some point, we just have to commit to a number here. So 20.1 degrees. And we still need the mass of the aluminum. So what we're going to do is we're going to transfer the aluminum block into the water, and then we're going to measure the temperature of the water. I did not grab one with a hole, so I will make a hole. We need to make sure that transfer happens as quickly as possible. Mess with that when we get there. All right. This temperature has changed. It has gone up. -7.3 degrees Celsius. Let's make the transfer. The string is on here, so I don't have to stick my head in boiling water. Let's see. That. I assume at least one of you can see the light. No, it's still going. Now we can keep, if we had it on the meter screen, we could just keep looking at it and see where it peaks. Doing it this way, we don't have to pay as much attention, and then we'll just see where the maximum temperature is. And shake it around a little bit to sort of mix the water up. Definitely seems to have plateaued. I'm leaking water too. Oh, wait a second. Okay. All right. So it's looking like it's peaking around, well, actually I should look at the whole thing. Let's stop. I don't think it doesn't want to. There we go. Analyze. Statistics, the red temperature. Max is 28.9 degrees. Now let's find the mass of the aluminum, and then we'll see how close we get to that prediction. I am going to assume that the string is massless or insignificant. 90 something grams. And the mass of the block is 92.70. Or 0.0927. All right, so cranking through this, what do you get as the predicted final temperature?
I got 26.43 degrees.
So I'm guessing Benjamin, you did not get the same thing?
I think I messed something. I'm getting 56.
Yeah, that does definitely not seem right.
I see. I put 0.9027.
Oh, that would do it. You had 26 point.
28.
I'm assuming that's a rounding difference.
Hopefully.
I got the same thing twice, so I don't know.
You got the 4.3? All right. We'll split the difference. It's somewhere in that ballpark.
Extra 0. Yeah, there it is.
Now, you know, I was expecting it to be a little bit closer than that, and I went back and I looked, and I realized that when I put the block in there, I got my probe that I'm put in there. If the probe is actually touching the aluminum block, it should start out initially higher, and then it'll cool down to the ambient temperature. And the temperature later on, when it levels off, is actually 26.4 degrees Celsius. So I would claim that we got it actually closer. However, it is what it is. It's a physics experiment, so we can always reduce our percent error by putting it into absolute temperatures in Kelvin, so that the difference gets washed out by the much larger numbers. Questions to hear? And Michael's going to settle the, you want to put money on it before Michael, oh, you realized another mistake?
Yeah, I did 9027 and then I switched it to just zero, it was like 0.09027
Ah.
instead of, yeah.
Okay.
So yeah, I got,
That wouldn't make me the tiebreaker, because my phone is known some pretty weird things.
Okay. So, the other thing while we have this here is, well, not that anything's showing at the moment, can you see the screen? I'm guessing that's a not really. Glare?
a little bit, yeah, that's better.
Take advantage of the differences.
Yeah, I got 26.43.
Okay. All right, is the glare a problem? Can you see the screen?
Sort of.
Sort of.
I can't like read the letters or anything.
Don't need to read the letters at the moment. All right, so the blue probe there, I'm gonna go ahead and start this. Blue probe is this one right here. It's right now at the very top of this. Is that better? Worse? Same?
Still same.
Same? And Michael, better?
Yeah, it's just as good.
Just, okay. All right, so I'm gonna hit, I'm gonna discard that data. All right, and it should be at somewhere around 100 degrees Celsius, I would expect, but now I'm gonna take it out and just let it sit in the air. And so it should be cooling off, and you see there, ideally, you're seeing it dropping down very rapidly, and then it starts to level off. So we've taken a probe, which was around 100 degrees Celsius, and we dipped it into basically air at somewhere around 20 degrees Celsius. And how can we model that cooling off there? Any initial thoughts?
Exponentially?
Okay. So I know that Q is equal to MC delta T. Let's make sure this is the path I want to go on. Yeah. Which is just MC T minus MC, whatever my initial temperature is. I know that MC times my initial temperature is just some constant for this particular situation. So, not yet. So if I take the derivative with respect to time, Q dot is equal to, well, the mass of the probe isn't changing noticeably. Specific heat should not be changing. Temperature is. And that's just a constant, so plus 0. I know that Q is equal to, oh, let's hit my notes here for a second. Oh, okay. I know the rate that at which heat will enter really depends upon two factors. When I have some heat exchange between the probe and the air around it, it depends upon what the material is of the probe. How quickly does it give up energy? How quickly does it take in energy? It depends on the surface area of the probe, because we have air hitting it from all sides. And it depends on the change in temperature. So this is also equal to some constant that is specific to the material times the area times the temperature minus the initial temperature. So if I set them equal to each other, I got MC d big T d little t is equal to H A T minus H A T I. Let's make sure I don't get a minus sign in the wrong spot. I do have a minus sign in the wrong spot. That is because, oh. If Q, I would expect if it's cooling, if the probe is cooling off, Q would be a negative number. It's losing energy. If it's cooling off, that means that the final temperature is less than the initial temperature. But as it gets closer to the ambient temperature of the surrounding area, I would expect the rate at which the temperature, the heat exchange, to be dropping off. So even though Q would be a negative number if it's cooling off, the Q dt would also be a negative number. Wait a second, let's suddenly talk myself around on that one. So the bigger T minus the temperature. Oh. It's the temperature of the environment. That drops off. If the temperature of the environment is less than the temperature of the probe, then there would have to be another negative in here. There we go. Because if the probe, this is the probe's temperature, this would be a positive number. But the rate at which that is changing should be getting smaller. So dq dt, the heat exchange will be becoming less. And therefore, it will be a negative number. So I have to have a negative there. So environment and temperature of the probe. I did not need to factor that, but I'm now going to solve. It's a first order differential equation. So I have dt over T environment minus temperature of the probe is equal to HA over MC dt. H is specific to the material. A is the area of the object itself, the probe, basically a cylinder. M would be the mass of the cylinder, and C is specific heat of the material. These two are actually part of with material specific, but in essence, for this particular problem, for that shape, this is just some constant, judgmental rate equal R. And I've lost the minus sign. Oh no, it'll show up here. All right, so I have the integral dt over te minus t is equal to r dt from some time from 0 to t, and this is from the whatever the initial temperature is to whatever the final temperature is, which actually should be that of the environment. What's the integral dt over te minus t? What does this mean?
ln te minus t.
Is that what you said?
Yes.
Missing one key thing.
Is that just the t in the front? Oh, times te minus t.
What's he missing?
It would be divided by t, but.
No, it would not be divided by t. All right, let's do use dust substitution here. So if u is equal to te minus t, what is du equal to?
Negative dt.
So this would become the integral of negative du over u. There's a minus sign. Hey, not throwing stones. All right, so negative natural log of that is equal to RT plus a constant. Since